In this tutorial, you'll learn how to create a physically accurate animation of a cannonball or similar type projectile using Blender's built-in physics and particle system. The setup will include automatic targeting and trajectory calculation using drivers, and a reactive impact debris splash effect. To ground the scene in physical reality, we'll first set our scene parameters to reflect real-world dimensions. Under the scene settings, set units to meters, angle to degrees, and make sure gravity is turned on and the z component at a value of minus 9.81 meters per second squared, which is gravity at sea level on Earth. We'll start by creating the cannon platform and gun barrel. For the cannon platform, create a circle with at least 32 vertices and change the XY scale to 2. Switch to top ortho view by pressing numpad 7, then 5, and numpad period to center the object. Tab into edit mode, and while in vertex mode, select the top vertex and pull it up on the y-axis outside the circle to create a point. This will serve as a direction indicator for the cannon's aim. Tab back into object mode. Next, create a limit rotation constraint for rotation x and y and leave the limits at 0. Then lock the transform rotations x and y. This restricts rotation around only the z-axis and level to the xy ground plane. Label the circle Cannon Platform. While still in top view, create a cylinder and set the dimensions to x 0.5, y 0.5, and z 1.5. Tab into edit mode and change the select mode to faces. Select the top face and delete it. This is the firing end of the cannon barrel, which should be open. Tab back into object mode and press numpad 3 for the side view. Move the cylinder up in Z to 0.75 so that the bottom is on the ground plane. Make sure the 3D cursor is at world 0. Now go to the Object menu, Transform, Origin to 3D Cursor. This will move the cannon rotation pivot to the back of the barrel. Next, rotate the cannon minus 90 in X so that it is aligned lengthwise to the Y-axis and aiming at the platform arrow. Click Object menu, Apply, Rotation and Scale. This will initialize the object's current rotations at 0 and scale to 1. We want the barrel's 0 rotation to be level to ground, and 90 degrees to point straight up. Label the cylinder Cannon Barrel. Then parent it to the cannon platform by shift-selecting the platform and pressing Ctrl-P Object. This next part of the cannon rig is for positioning the cannonball emitter inside the cannon barrel. If the emitter is positioned near the back of the cannonball object will appear to pass through the front edge of the barrel as it exits. This is because the physics simulation is moving the ball downward under the influence of gravity immediately upon creation. To prevent this, the emitter must be positioned near the front of the cannon barrel. A more distant target and greater launch velocity will result in less vertical displacement along the barrel, so the emitter can be positioned farther back. Create an empty sphere type. Scale it down to 0.25 to fit within the cannon barrel diameter. Next, move it up so that its top is even with the top of the cannon barrel. Label it Emitter Constraint. Parent it to the cannon barrel by selecting the empty first, then the cannon, and pressing Ctrl-P, Object, Keep Transform. Reselect the empty and lock the empty rotations and location X and Y. Create a limit rotation constraint on the empty and set the X, Y, and Z axes, min and max, to 0. Then check on For Transform and select Convert to Local Space. Create a limit location constraint and set X and Y min and max to 0. Set the Z location min to 0.25 and the max to some value outside the barrel, like 1.75. This will permit some flexibility in setting the initial emission position of the cannonball. Set the limit location constraint also to For Transform and Local Space. For the particle emitter, create a plane object and scale it to 0.25, the same size as the emitter constraint or smaller. Name the plane object Cannon Emitter. Then add copy location and rotation constraints to the emitter and choose the emitter constraint as the target. The cannon construction is essentially finished, but we need to set up some constraints to restrict movement of the barrel to rotation on the x-axis only. This is the tilt axis for changing the cannon aim elevation. First, let's move the cannon barrel up above the ground 0.75 meters in location Z, then lock all location axes and rotation Y and Z. Create a limit rotation constraint and set the X-min to 0.1 and the X-max to 89.0. The cannon rotation must be limited to this range to prevent calculation errors in the emitter driver. Plus, it doesn't make any sense to aim below ground level 0 or 90 degrees straight up. Set both Y and Z rotation, min and max, to 0, then check on For Transform and select Convert to Local Space. Create a limit location constraint and set the X and Y min and max to 0. Set the Z min and max to 0.75. Then again check on For Transform and select Convert to Local Space. Before we begin setting up the particle emitter, we need a cannonball object as a particle stand-in. Create an icosphere and make it the same radius as the cannon barrel or less, such as 0.24. Label it Cannonball and move it to the side of the cannon platform. Now let's get the emitter working and shoot some cannonballs. Select the cannon emitter plane. In the particle properties, click the New button to create a new emitter. Rename the setting Cannonball Emitter. Set the type to Emitter. Set the number of particles to 4. Start frame can be 1 and end frame can be 200 for now. Set lifetime to 200 or more. Emit from faces and jittered, and set particles per face at 1. For velocity, set normal to 15 for now. Set physics to Newtonian, integration to midpoint. Time step should be 1 divided by the scene frames per second. So if your animation frame rate is 24 frames per second, enter 1 divided by 24 in the number field, and it will calculate the proper value. Under Render, check Emitter off so that the emitter plane does not appear in the final render. Select Object from the option buttons. In Dupli Object, select the Cannonball object. This will substitute the icosphere cannonball object for the particle. Check Scale on and set Size to 1.0. Then under Field Weights, Make sure gravity is set to 1.0. Finally, it's time to test the cannon. Aim the cannon barrel at an angle, set a platform direction, and click the Animation Controls Forward button, or press Alt-A to start the simulation. Next, we'll create a targeting mechanism which will allow us to position the cannon and the target anywhere we want, and always hit the target. Create an empty to be the target object for the cannon, and label it Target. Make it a circle empty this time, and change its size in the empty properties to 0.5. Then rotate it 90 degrees in X. Move it some distance away from the cannon. Select the cannon platform and create a locked track constraint. Choose the target empty as target and set the to axis to Y and the lock to Z. You should see a relationship line drawn between the platform and the target. If you don't see it, open the display options in the viewport properties and check on relationship lines. Now you can move the cannon platform or the target anywhere you want, and the platform will rotate to aim directly at the target. The cannon barrel does not adjust its launch angle, since that is manually chosen by the animator. The only remaining parameter affecting the targeting is the projectile launch velocity, which will require a driver, so that is what we'll set up next. The velocity calculation is derived from the standard physics formulas for a projectile in 2 dimensions. I won't explain the details of the equations, but I'll display them for reference. We'll start by creating the driver for the emitter velocity. Select the cannon emitter and display the particle properties. Under Velocity, right-click on Normal and select Add Driver, Manually Create Later Single. Pull out a new vertical panel from the viewport and change it to the graph editor. Then change the view mode to Drivers. Select the Normal property in the object list and click the Drivers tab. For the driver type, select Scripted Expression. In the Expression field, type in the Python expression as displayed here, or mouse copy it from the video description of this tutorial and paste it into the Expression field. We'll need to define 4 variables to satisfy the expression. The first variable is g for gravity. Enter g in the variable text field, then click on the option menu to the left and select Single Property. In the property menu below, choose Scene, then click on the text field and choose the current scene. In Path, type gravity and the number 2 in square brackets and enter. You should see the value update to the current gravity z value of -9.810. Next, click the Add Variable button to create a new variable. Name this variable A for the vertical launch angle of the cannon. Change the variable type to Transform Channel. Select Cannon Barrel for the object and set the type to X rotation and space to world space. For the other 2 variables, we need to first create some custom properties on the emitter. Select the cannon emitter and under the particle properties, open the Custom Properties. Move it up on the list so you can find it easier. Click the Add button to create a new property and click the Edit button. For property name, type Target Height. In the min and max values, enter a large negative and positive value that is beyond the vertical range of your scene. In the description, type vertical distance between emitter and target. Then click OK. Right-click in the Target Height field and select Add Driver, Manually Create Later. For this property, we are going to create a driver to calculate the vertical distance between the cannon emitter and the target empty. This result will become the height variable for the velocity driver. Select the target height property in the driver property lister. Make the driver a scripted expression type. Name the first variable target zlock. Choose single property as the type and choose cannon platform as the property. For the property path, we're going to follow the path of the platform target constraint to the object that is currently assigned as its target. Currently, the empty we assigned and named target is the target object. But if we want to change the target object, we don't want the driver variable to reference a specific object. We want it to reference the constraint target, whatever it is, and its world z position. So we are going to reference the constraint target path, not the target object itself. So first select the cannon platform, then find its track constraint, and right-click on the target field. Choose Copy Data Path, then reselect the cannon emitter. Click in the Target Height Path field and paste in the copied path. The path identifies the object type as constraints and the specific constraint as locked track. Then it refers to the target property, not the current object assigned as the target. Don't confuse this with the empty we assigned as the target and named target. Now we still need to reference the target property's height, which is its z location. So after the word target, type .location, then the number 2 inside square brackets. This is the Python array index for the z component. You can tell you have entered a valid path when the path color is white and the value is a valid number. Now add a new variable. Make it a transform variable and name it emitter zloc. For object, choose cannon emitter. Choose type zlocation and world space. In the expression, enter target zloc minus emitter zloc. Now you should see a result calculation in the target height property of the emitter. Next, add another custom property. Name it target distance and description horizontal distance between emitter and target. Set the min and max values to a large number beyond the extent of your scene. Create a driver for this variable and select the property in the driver lister. For this driver, we are going to calculate the horizontal distance between the emitter and the target. We'll use the Pythagorean theorem, which determines the length of the hypotenuse of a right triangle given the two smaller sides. The sides of the triangle are the difference between the x locations of each object and the difference between the y locations. This forms a triangle on the xy plane. The horizontal distance between the objects is the hypotenuse of the triangle. That distance equals the square root of the sums of the squares of each side of the triangle. So the expression will be square root of xe minus xt squared plus ye minus yt squared. The invalid expression alert means it contains unrecognized variables, which we will create next. We'll start with the emitter values. Select the transform channel type and name it xe for the emitter x location. The object is the cannon emitter. Type is x location and world space. Then add a new variable. Make it a transform type and name it ye. The object again is the cannon emitter and the type is y location and world space. Now for the target variables, we are going to reference the platform target constraint as we did for the other custom property. Add a new variable, a single property type, and name it xt for target x location. For the property, choose the cannon platform. In the path, paste in the data path we copied earlier. To the end of the path, append dot location left bracket 0 right bracket. If the value does not update properly, click the Update Dependencies button at the top of the driver panel. Add the last variable and name it YT. Repeat the same steps as for the previous variable, but append the path with .location 1. Now the driver expression should display a new value. Now that we have our last two variables for the velocity expression, we can complete the velocity driver. Select Normal in the Driver Properties list. Add a new variable and name it d for distance. For the property type, choose Particle and Cannonball Emitter for the object. Copy the data path from the custom Target Distance property and paste it into the path field of the driver variable. Notice the variable value should reflect that of the custom property it is referencing. Add a new variable and name it h for height. Repeat the same process as for the previous variable. When this is complete, you should see a calculated driver value above and in the normal velocity field. To test the system, move the target and cannon platform around and tilt the cannon to a new angle. Then run the animation timeline. Add a new object, such as a cube, and move it some distance from the cannon. Then go to the platform constraints and change the track target to the cube. Switching the target in the constraint is a convenient method of changing targets, but if you want to re-aim the cannon during an animation, you have to animate the target to the new position. Be aware that if the height of the target exceeds the straight line angle of the cannon, the velocity expression will fail and evaluate as 0. When this happens, you must move the rig into a valid trajectory and press the Update Dependencies button in the driver to reset the system. Now let's add some ground geometry for some physical interaction. We'll add a ground plane for the cannonball to interact with and name it ground. Scale it up to contain the cannon and target and move the target height to the ground plane level. Let's give the ground a material color to separate it from the other objects. Now go to the Physics tab in the Properties panel and make the plane a collision object. When we play back the simulation, the cannonball bounces off the ground. Suppose we don't want the cannonball to bounce off the ground, but disappear when it hits. To do that, go to the Particle Properties and under the Physics Properties, check on Die on Hit. If you still want to see the cannonball after it has hit the ground, go down to the Render tab and check on Died. For some added realism, some reactive impact debris would look good. For that, we need another particle emitter. Create a plane object and scale it a bit larger than the cannonball diameter. 1 meter wide is good. Name it Impact Debris Emitter. Then move it away from the cannon and raise it up slightly above the ground plane by 0.1. Open the Particle Properties and create a new particle system. Name the setting Impact Debris. Set the emission number to about 300. Set the start frame to 1 and end frame just a few frames later. Set the lifetime to the end of the animation. Emit from faces with even distribution and random. For the emission velocity, use the normal setting and give it a value of 4 and a random setting of 3. Under Physics, set to Newtonian and a mass of 5. Check on Multiply Mass with Size. Time step equals 1 divided by your scene frames per second. For the render settings, check off Emitter so the emitter plane does not render. Select Object and Duplicate Object to Cannonball for now, or you can create your own irregular geometry to function as the shape of the debris fragments. Check Scale and Size to about 0.15 and Random to 1. Then set Display to Render. You should get a varied distribution of fragment sizes and distances. To control the reaction of the particles on the ground plane, select the ground plane and its physics properties. Turn the particle damping up to 1 and random to about 0.5 to control the bounciness of the fragments. To control the sliding, set the particle friction factor to 0.1 and the randomness to 0.25. Now we just need to aim the cannon at the debris emitter, so select the cannon platform and the constraints properties and set the track target to the debris emitter. To adjust the timing of the debris splash, set the debris emitter start to the frame when the cannonball dies on impact with the ground, and set the emitter end just a few frames later. We can calculate the impact frame using drivers, but unfortunately Blender doesn't allow these frame properties to be controlled by drivers, so we still must input the correct value manually. To do this, create a custom property on the debris emitter and drag it to the top of the property list where we can see it. Edit the property and name it Impact Frame. Set the min and max values outside the frame range of your animation. Now add a driver to the property. In the expression field, enter this expression. 24 is my animation frame rate. If your scene frame rate is different, enter that instead. We will need 3 variables for this driver expression. The first one is the aim angle of the cannon, so label it A. For the object, choose Cannon Barrel. For type, select X rotation and world space. The second variable is the launch velocity of the cannon emitter. Make this a single property type and label it V. Choose Particle in the property type and Cannonball Emitter for the particle setting. Since we are using the normal velocity type on this emitter, just enter normal_factor for the path. The last variable is the horizontal distance between the emitter and target. Use the single property type and name it D for distance. We already created this custom property for the cannon emitter, so choose Particle type again and Cannonball Emitter. Select the cannon emitter and copy the target distance property data path. Then paste it into the debris emitter driver variable path. Now, wherever you move the cannon or the target debris emitter, you will know the exact frame when the cannonball hits the target. Then just enter that into the emitter start frame and add 2 frames for the end frame. To create an impact against a wall, just rotate the impact emitter parallel to the wall and move it near the surface. Make the wall a collision object so the cannonball doesn't pass through. Hopefully, this will give you some ideas for experimenting on your own to create some exciting and realistic projectile animations. In Part 2, we will modify these techniques to animate arrow and spear projectiles. Thanks for watching.